This is an attempt to be a really complete overview of exponential random graphs, which means I have packed a ton of information in 90 minutes. We'll see if I get through all of it. So with that in mind, you're not expected to get everything from all the slides. The idea is that the slides should also be a resource for you to take home to use in your own research. I mean, if you find you have a problem and you want to use exponential random graphs and you want to go back through the theory and remind yourself. Okay, so there's a lot in here. Feel free to slow me down, stop me, ask questions. I have a new 3.5-month-old, so I'm maybe even a little more jittery than usual, so I apologize. But in general, we're going to do a lot. So I want to start by just talking about basic preliminaries. My slides have a lot of R code embedded in them. Not a ton, but enough to sort of help get you pre-prepped for the lab. And so I will work from 3 basic packages. You'll notice I have statements throughout calling the StatNet suite of packages. And StatNet is this large team of research collaborators, including, of course, Jim Moody, and they've put out a great set of software, and we're going to build from that set of software. And it contains a whole bunch of different R packages. We're only going to focus on 2 in this case. I don't know, have you guys used the StatNet suite at all yet?
Yes.
Little? Okay, so you're familiar with the network objects, hopefully? That's sort of the key thing here, because I wasn't planning to really go into the network objects. So ERGM works entirely on network object data. And so as long as you've got something in the network object, you can stick it in ERGM. And so that's sort of basic assumption. CODA isn't actually by the StatNet team. It's a general software package for checking MCMC data. And so obviously Alex talked about MCMC methods, and I'll talk more about that. Yeah, that's the basic preliminaries. Everybody feeling comfortable? We're going to kind of move forward. Okay. So as always, right, with these things, it's good to make sure we're all on the same page. We all understand the same notation. We're going to go through just a basic reminder of network data. We have sort of these classic forms, right? We have the binary adjacency matrix, many of you have hopefully been seeing all week. We have sort of these classic image plots, and then we have the sociogram, or sort of classic network plot, right? Where the nodes are the entities that we're interested in. These are often actors or respondents, but they can be organizations, they can be animals, plants, computers, whatever. And then edges are some sort of relationship. This could be friendship or needle sharing, sexual contact, that sort of thing, right? And they can be directed or not directed. They can be valued or dichotomous. We just saw a large presentation on some very clever things you can do with valued data. And there are some things you can do with valued data in the ERGM framework. I won't talk about it here in this lecture. It's mostly all in progress work. So this will all be on just simple binary data. All right, so looking over your guys' schedule, you've done a bunch of stuff with respondent-driven sampling, network sampling kind of stuff, right, in the last week? So you've done a lot of sort of classic design-based network inference. You've looked at sort of classic descriptive statistics and that sort of idea. Today, just like Alex, we're going to focus on statistical modeling. We're going to focus on sort of key ideas that you can do with these models, right? So we can test, we can evaluate competing theories of network formation and generative models for networks. We can estimate parameters of interest. We can use it to describe and understand the network better. And we can also use it for prediction and simulation, right? So we can use it to impute missing data. We can use it to predict other network structures, that sort of thing. Okay. So in any sort of model-based framework, we have to think very carefully on what sort of model is important, what sort of features of the network should really be driving the network formation. And so there's a bunch of classic literature on this, right? People describe, are interested in things like reciprocity, popularity. We have transitivity, triangle clustering. We have, these classic ideas of stochastic equivalence and node partitioning, and issues of homophily, male, female homophily, or age homophily, like in the ad health data. And so we can kind of think about these larger terms, and these are some of the ones that we'll talk about throughout this lecture. And this is just sort of to get your mind thinking about model building, right? There are lots and lots of important theoretical things, and these are all going to depend on your particular problem at hand. And so, maybe what's really important is reciprocity. We're interested in, say, countries in the world and how they interact in military disputes. And so we want to know if one country attacks another, are they really likely to attack back? Maybe we're interested in degree heterogeneity, right? We're working in some sort of like Facebook type network, and we expect some idea of preferential attachment to be occurring, right? Super popular people are going to collect tons and tons of friends, and other people are going to have a few or none, and we want to capture that sort of thing. Maybe we expect a lot of homophily going on, like in ad health, we see a lot of age and gender homophily, or maybe racial homophily. Transitivity, right? This idea that a friend of a friend. So if I'm friends with Bill and Bob, I might expect Bill and Bob to also be friends. We might have a triadic closure bias going on. We might expect some idea of balance, right? If I dislike Bob and Bill dislikes Bob, then I might expect me to be friends with Bill. And then we can have these ideas of equivalence, right? Maybe we have some organizational structure network, and we expect managers to be like other managers. And that sort of thing. So with that in mind, I'm going to take some time out to show just some pretty graphs. This has sort of two pieces. One, to sort of get us to think about how we want to work on model building, what sort of different properties we might expect in different networks. And two, because I've got a lot of text-filled slides for the next hour, I want to have some pretty pictures to get you motivated and keep you going. So this is a really classic data set. This is military disputes, right? Maybe we're really interested in reciprocity or clustering or degree heterogeneity. Maybe some countries are really getting ganged up on. This is IRS migration data. So this is data for 2000, 2001 in the US. It's all the counties, and to get the binary data, it's a cutoff of 99%, so it's only the top 1% of sending and receiving interactions. And so you'll see there is a few counties that are like a really big deal, and then most counties are just either sending or receiving a couple. So you might be interested in some sort of cluster analysis here. We of course have the classic ad health kind of data. This is actually a simulated data from an ERGM. So the StatNet team, when they were looking at ad health. And ad health data, as many of you know, right, is not actually easy to get the base data. It's very protected because it's super sensitive data about all of these students. And so one thing they did in the StatNet suite is they give a simulated poll of a network actually fit to real high school data. So you get something that has approximately the right properties that you can sit and play with, but doesn't have any of these identifiability issues. And so this idea is a pretty cool idea as far as like masking really sensitive data, but still letting people play with it. But for here, it's sort of a classic example, and we see our gray level homophily effects. World Trade Center communication data, right? And health communication can be really important. You can think about organizations interacting. I guess I moved it. Next slide. So, this is sort of a classic hub-spoke model, right? This is radio communication. We have sort of classic friendship data, right? And notice that a lot of classic friendship data is directed. So you could have friendship data like Facebook, right, where you can't have questions of reciprocity. But if you give people a survey, and Bill and Bob don't have to nominate each other, even if Bill nominates Bob, Bob doesn't have to nominate him back. So friendship is maybe a reciprocal relationship or maybe not, depending on you measure it, right? And so measurement affects how you're going to model things. I like bringing up this example. This is an emergency response network. A bunch of different emergency response networks, but this is a very sort of nice organizational health sort of relationship, right? So these are actually things like EMTs and firefighters and police responding to a disaster or some sort of event. And you have these same sort of team problems and a lot of organizational health issues, right? People pair doctors and nurses and specialists together to all manage single patients, and you want to know how these people work together and care and whether you've got sort of the optimal case for the patient. And so there's a lot of these sort of organizational ideas that can be modeled in this kind of framework. Okay, so hopefully we're feeling a little motivated, a little jazzed. Networks are fun, right? We're here because networks are fun. They're a pretty powerful idea, but there's a lot of details and a lot going on. So we have our classic, say, network data with our adjacency matrix, and maybe we have some covariates X. Before I get into the sort of autoregressive framework of the exponential random graph model, I want to bring you back to just the basic logic of modeling. I've kind of been, when I put together these slides, working from the basic idea that all of you guys have seen linear regression, maybe general linear models in one of your stats classes. Is that a reasonable assumption? I'm seeing a lot of heads nod, so I'm going to take that as a good sign. I realize it's still morning, and I'm coming from the West Coast, so it's still really morning for me. But okay, so we have, right, the classic regression or generalized regression framework where we have some y's on some betas of interest, some covariates, and maybe some sort of stochastic relation. And we can use this in a lot of clever ways, right? We saw this morning sort of the latent space models, and it's really built from sort of a similar framework. These ideas, right? Once we have a probability model, we can impute missing data. So that's really cool, right? Because in the real world, so you did some sampling network data, but if you've noticed, right, when you talked about a lot of the descriptive statistics and networks, they were almost all on complete data, right? You had magically the entire network, and then you computed some sort of path score or something that you were really interested in, right? Or the triad census for the entire network. But in the real world, you almost never have complete data, right? You always have a couple edges missing. If you're really unlucky, a couple nodes. And so that brings in complexity, and you want some way to handle that. And so one of the nice things, right, with working with a probability model, just as Alex implied, you can now impute your missing cases and get a sort of holistic estimate for what's going on. You can even just use the imputation to get back to your basic descriptive statistics, right? If that's really what you want to do, is the basic network descriptives are what you care about, but you have just partial data. You could use something like an ERGM to fill in your missing data and then compute your descriptives. Okay. So this is just to warm us up to this modeling framework. Nothing super deep here, but there's a lot of moving pieces, right? Okay, so we're going to build up this particular statistical model for social networks. Obviously, this is just a statistical model for social networks. There are a lot out there. This is a very powerful one, though. It's got a very rich language. So we have our standard, right, social network, and we've got our Yij edge, where 1 is our relationship from actor I to j, 0 otherwise. We usually work with the, say, full matrix. I'm going to use capital for the population of all matrices, right? This is our random variable, and then little y for our observed matrix. So the basic problem here in this framework is we want to know what is the probability that we saw our observed network given the population of networks, which is in itself sort of a weird idea if you think about it. This is sort of, in some ways, you can almost think about this as like a weighted earn model. This is a really goofy description, so ignore it. It doesn't help you. But this is the idea, right? We have all possible graphs. Say we're interested in a really small network, say size 3, right? This is just about the smallest network that has some interesting properties. Combinatorially, there are, if it's undirected, right, 3 choose 2 possible combinations if you want the whole network space, right? So there's 6. Now, there are 6 possible networks, but maybe not each of those 6 networks are equally likely, right? We expect some sort of weighting based on features. So we imagine, say, that there's this triadic bias closure. We expect everybody to be connected or nobody to be connected, right? So we want to put some sort of weight on the number of 3 cliques. So this G of Y represents any network feature. So it could be triads, it could be degree, it could be more complicated centrality terms. It's just whatever feature we care about. And it happens to be in this particular statistical model, that's also the sufficient statistics. So that's a lot of weight to put in a little function. But I want to go back to this idea of all possible networks, right? So our really simple 3-person network, right? We can, in principle, build up just a simple, naive combinatorial probability, right? So we want to know how likely was our observed 3 network that we actually measured, given all possibilities where we know certain properties are more likely, right? So what is the naive way to do this? Well, the naive way to do this is we want to guarantee we have something that's a probability. So that's why we have this exponentiation term. It forces everything to be positive, right? And then we have our weight. This is just saying whether certain features are more likely. Then we have our features of interest, so say just a simple weight on the 3 cliques. And then under here is going to be all possible things we could have seen correctly weighted, right? So it's going to be the same exponentiated model, but summed over the entire space. Okay? So, I mean, in some ways, this is beautiful in its childish simplicity, right? We're literally just taking what we care about, what we observed, and dividing it by all possibilities, and then that is our probability, right? It's just a counting exercise. What happens if our network's big, say 10 people? Are we going to be able to compute all possibilities even on a network of size 10? The answer to that is no. No, we are not. It will take our nice computer, until the sun explodes. You can do this up to graphs of size 7, basically. Computers are improving. I'm sure it'll eventually get to 8 or 9, but we're not going to do it for a general size node network. And so this is where ideas of MCMC are going to come in. And I'll talk more about how we deal with this problem in a lot of ways, this slide and this point in the lecture is a big tease, right? So I've got you working and thinking about this very general, complete model, right? But people didn't start here. This isn't where we start, right? So with that in mind, I want to go a little bit back in time and do just a very brief history lesson focusing on a couple key models that I'm going to use to build up the general case. And, you know, because I'm an academic, I like giving just a little history. Okay, so the simplest model to sort of build from and think from is a Bernoulli graph, or an inhomogeneous Bernoulli graph, if I want to let every edge be have a different probability, right? So this is sort of the idea that networks are represented by a simple biased coin flip, right? And we just want to figure out how to find what the bias is. Or, because I'm just working from pure probability models, right? I haven't talked anything about inference yet. If we know what the bias probability is, we can stick it in our probability model and we can compute out the results. And you'll notice from the way I've written this up that this is going to be connectable to sort of standard logistic regression. And this is just sort of foreshadowing where I'm going. And so this is sort of the first simplest network model that a lot of people started with. And this has certain appeal if all you're really worried about is basic density parameter and maybe some exogenous covariance. But right, this is an edge independence model. We can't handle issues like triadic closure bias. So the next extended model was so-called Holland and Leinhardt's P1 model. You'll notice that this bears a remarkable similarity to the stuff Alex talked about. This is the same basic, the simple model, right, where we simply have a term for edges, a term for reciprocity, and then we have a sender and receiver effect, what they called productivity and attractiveness. And so they showed that this could be fit using a multinomial model. This is allowing for just interdyadic dependence, but no like triadic closure bias, right? We can't go to second or third order terms, but we can handle the within dyad problem. And this is pretty cool. This is very, very clever. Lots of things have spawned from this, obviously. One of them is one of the original names for the exponential random graph models. In some of the past literature, you'll see people use what they call the P-star model, which is just the exponential random graph model. What happened was a couple people who worked, or no, more than a couple people, a lot of people who built onto this into the general case worked from some people who had a really, I don't know if clever, but had a very specific Unix joke. So for those of you who know that the star means and anything, so they called it P star. So you will see that notation sometimes. It's been largely subsumed, though, by the current ERGM nomenclature. After that comes Franken-Strauss's nodal Markov statistics. This allows us to get even more sort of issues of symmetry and sort of compress the model. It turned out these didn't work very well for like any social data, so I'm basically just going to skip on. Okay. Had this brief history lesson. I'm skipping over a very important area that I'll talk a little bit as I build up these models. It's called the pseudo-likelihood estimator. It's really part of the inference section. But basically, it's an idea of extending the Logit model to try to fit ERGMs directly and ignore that complicated denominator. Turned out it didn't work very well, and that's mostly why I'm skipping it. But there are a few important ideas in it that I'll talk about. Okay, so let's go from the Logit case, right? So The simplest, most basic ERGM that we can work with is the simple Bernoulli graph model, right? And so we can sit down and we can write our standard logistic regression type model, right? Where the function, right, that maps us into the logit, which maps us from the discrete space to the continuous space, is this logit function. And if we assume it's linear in that, we get our standard case. And so we can handle a basic density term, right? A simple probability of the edge, how likely it is for any two people to interact. And we can handle sort of arbitrary exogenous covariates, right? So these may be issues of homophily. We can test, gender homophily or racial homophily, grade homophily, that sort of thing. But we can't handle any of these sort of complex feedback loops. I'm sort of skipping over the basic inference problem, right? I'm doing two things here that is maybe a little confusing. We haven't said how we get these thetas, right? So we're saying we have this population of networks, they're weighted by features we care about, and if we know how those features are weighted, we have a probability model to work with. That's of course never what we do in the real world, right? This is sort of a statistician's way of building up a concept. So we have population parameters, and we want to do classic statistical inference, so we're going to, of course, estimate them from our observed data. And so when we've got this simple logit model, we can infer this from classic logistic regression. It takes a little bit of work, but you can actually just stick this in, say, the logistic regression function in R. Luckily, people have done this work for you. And I'll walk you through very briefly in a couple slides how you do this in the ERGM framework. Because there is some details for, say, pulling apart these x's, right? Because you have a matrix and you've got to just decompose it into vector form. Okay. Everybody pretty much okay with that? Hopefully, this is basic ideas you will have seen somewhat before, just explained in a slightly more confusing way, right? So some basic important points. Interpretation's great. We get our standard logistic regression interpretation right. We can interpret it as an odds ratio or nods. But we've got this really crazy strong assumption that our edges are independent of each other. There's two ways to fit this in the StatNet package. I'm just going to talk about the ERGM case. Okay. So for the examples, because these are readily fit, this is a small network, and it's sort of one of these classic ones used to demonstrate this. I'm going to use the Florentine families data. Have you guys seen this already? No? Okay, so Padgett, back in the day, collected all of this very cool data on these Italian families, the Florentine families, and so he collected marriage data and business data and some other things. It's neat, but it's a small, easy to manage network, and so I can show the basic structure here. So we can fit, right, the flow marriage, this is a network object. We use this tilde sign, and then these are the network features, okay? So edges is the density term, this is the basic intercept. I'll make this sort of crystal clear why this is the case, but in a few slides. And then we have just basic node level covariates, right? These have to be exogenous, so in this case, we're looking at the sum of wealth. So we look at the sum of the wealth between two families and say, are they more likely to be married or less likely to be married, right? We're going to look at sort of whether the this weights up or down likelihood of them being married, the families being married, not individuals. I want to point out these are families. You know, you wouldn't ideally look for triangles if this wasn't families. There aren't a lot of societies that have marriage that way, and certainly I don't think Italy at this time. And you can look at the absolute difference of wealth. You can look at a lot of different things. There's a general language within the ERGM terms for basically adding any covariates, assuming you've got it attached to your network object correctly, right? We'll go over how that's connected in the lab, but I suspect many of you have seen this already. I see any heads shaking? See a couple, okay, it's promising. Okay, so we fit them, we get out the formula, and then we get out the estimate. These are the theta weights, right, on log scale. We get a standard error. We get this MCMC percentage, but of course we're not fitting this by MCMC methods right now, so this should properly be 0, and then we get our standard like p-values, right? And so what does it mean for a parameter to be 0 in this case? Remember, this is logistic regression. If it's 0, it means that we have just a basic coin flip, right? Everything is benchmarked on 0.5, which is nice, right? We just say, you know, it's got a random chance. And we also get our sort of classic BIC output. Have you guys been taught sort of likelihood-based model fit criterions? I'm not going to talk too much about it. BIC is one way to make a decision between which model is better. Lower is better. So whichever BIC has smaller, that's the one we say is better. So this one says model 2 is a better predictor. You know, this is sort of the same idea, or it's related to sort of the adjusted R-squared measures and stuff you see in simple linear regression. There's a lot of issues in model fitting and stuff, but this is a nice first way to start. So, you know, we see this basic thing, right? We see that two families are very unlikely to be tied, right? Our basic density measure is really low. And then we see that we get a small boost for wealth, although notice wealth is, right, a continuous variable. This could be quite large. 0.01 times a large number is still very large. And the absolute difference in wealth is you know, slightly bigger, but you know, there's some limitations to comparing across models. Okay. So that's a lot, but we can at least fit the basic logistic regression. We know that it's got sort of our standard interpretations, and we're feeling pretty good. Okay, so obviously the goal here is to go beyond this, right? We want to work with this general framework where we can look at any of these larger feedback characteristics, right? Triangles, stars, etc. Okay, so how do we do this? Well, as hinted earlier, right, we can basically extend this to a full discrete exponential family model. Turns out this has been used a lot in things like statistical physics, and it has some known properties and some known problems. So that's both, you know, good and bad. Hold on. Sorry, I just want to check and make sure I'm doing okay on time. Okay. So let's remind ourselves of the basic exponential family model framework that we talked about earlier, right? We talked about this probability of a graph. Notice this is the probability of a single graph, right? We have the graph that we went out and measured in its entirety, and then we have this probability model, right? So we have our observed statistic, or observed case divided by all possibilities. And ignoring the fact that we have to figure out how to get an estimate of this, if we could, we would go and do sort of standard maximum likelihood estimation to get our theta, just like we did in the logistic case, right? But notice there's one really weird thing that I've been saying here. And we're calculating the probability of the entire network, right? In practice, in our research, we don't very often say, oh, this network we were likely to have seen at 20%. I'm now going to interpret that for any sort of social science implication. Like, it has it, we could probably logic through, but that's not how we usually think about things, right? We generally think about things about the probability between two individuals, right? So we're worried about people, say, sharing needles, and we want to know what's the likelihood that Bill and Bob are going to share needles, and then we want to come up with some intervention to stop that from happening. Or we want to pass through some new health idea, right? We found a fancy new condom, we want it to pass through the network, and so we want to make sure the communication patterns are dense and available. And so we're going to want to know that Bill and Bob are actually going to talk. Fundamentally, we want to talk about things at the edge level, not usually at the full network level, right? The population of networks. So we're going to have to do some work to get to that point, but the work is really worthwhile. It's going to give us two really fundamental things. It's going to give us a way to interpret our parameters that is sort of understandable and useful. And it's going to basically frame how we're going to do our inferential framework too. So it's one of these really important ideas. We move to it, and it will move us into our maximum likelihood estimation. So hopefully the order makes sense as we sort of go through it. It's a little backwards in the sense that usually you do the inference model and then you talk about the interpretation. We're going to go from the interpretation to the inference model. Okay, right? We're going to express this local view of the world. Okay, so to do that, I'm going to have to introduce some notation. But this is really important notation, and this is going to make a lot of the model a lot more understandable. So I'm introducing three key things. We have this y plus ij. That's the case where I've forced the ij edge to be 1. We have this y minus ij. This is where I force the ij edge to be 0, right? So I'm turning it on or off. And then I have this y ijc. And this is going to be the entire network except for the ij edge, okay? Right, I'm going to build up a conditional probability model. Okay, so I'm going to re-express my probability of the graph as the probability that the edge is equal to 1, right? This is usually what we want, or we want the Logit comparison. So the nice thing about this, when I rewrite it in this way, you'll notice a few things. I get rid of the annoying denominator. Everything's sort of expressed in a cute little way, but I can make this better, right? I can look at the logit of this, right? So I can look at the log of the conditional probability, and I get this thing here, okay? This thing here is what we're going to call the change statistic. This is pretty nice, right? So we have our parameter weight times our features with the edge forced to be 1 minus the case where our features with the edge is forced to be 0. So this gives us sort of a standard odds interpretation, right? So let's do a very simple case. Let's look at the Logit form. And this is going to make one thing really, really obvious, and I find this to be a really nice thing to point out. So right, we have the logit of our yij equal to 1, conditioned on holding the rest of the network fixed. And then we get simply our theta weight times our change statistic. Well, the change statistic in the edge is just 1, right? Because we've toggled it on minus toggling it off. So theta times the edges term is our basic density parameter, right? So that's why the edges term in the ERGM model is our simple intercept term, okay? That's pretty cool. It gives us this basic way to interpret all the thetas right as a conditional probability model. However, this is not a like fix-all, right? So how do I want to say this? One really obvious, naive idea, right, is to take these change scores, stick them in our logistic regression model, and just fit our ERGM that way. Turns out that doesn't work. It, as Alex said, in the sort of best case, it's bias. In the worst case, the variance is also just terrible on the parameter. So you get something that's both biased and the standard errors are estimated wrong. But that idea has a very important component. That's what they call the pseudo-likelihood estimator. And the pseudo-likelihood estimator will come back up in how we fit ERGMs. And it's also just an important estimator to know. It was also used in spatial statistics, although they also discredit it. It, in general, is like this beautiful, simple idea and doesn't tend to work very well, which is sort of unfortunate. Right, and why doesn't it work well? Well, it has this basic problem, which is we've got this model that can't handle having y on both sides, right? We have an autoregressive problem, right? When we put the count of triangles on our right side, we're taking information from our left side. And if we don't account for that, our model is going to be bad, and indeed it is bad. And so we need a way to handle this feedback, this dependence in the network. The fact that the edge actually, the likelihood that any two individuals are interacting depends on other people in the network and their interactions. But that being said, this is a really, really useful aid in interpretation. This is the primary tool that people use for interpreting the ERGM parameters. And we'll talk more about this in the lab, but this is sort of something to keep in mind. Okay, so now we have this probability framework. We can frame our theoretical ideas in the networks, right? We can sit and write down what network features we think should bias the network. We can go and compute, in theory, at least very simple probability model if we know the thetas, or if we had a way to compute the denominator. So we're now going to deal with those two problems, and we're going to deal with it in a sort of standard maximum likelihood way. Okay, so we can write down the likelihood, right? The likelihood is the probability of our observed data, and we want to know what thetas maximize what we actually saw, right? This is the basic likelihood principle, the idea that our parameters of interest should be the parameters that say what we observed is most likely. But we're back to this basic problem. We can only do this for networks up to size 7. So we're great as long as we're interested in very small preschools, right? Very small preschools, we can literally just go and calculate this likelihood. We can do our model comparisons. We're, feeling pretty good. And then we realize, oh, what if I wanted to do this classroom right here? I'm kind of SOL, aren't I? Okay, well, turns out there's been some very smart people working on this problem for a long time, and there are some very good solutions. The solutions depend on modern simulation techniques. So these are computational techniques that have really taken off in the last 20 years, maybe 30 years. Basically, as computers have gotten faster, we've been able to do what they call MCMC pretty readily. And there are lots and lots of software for sort of doing this out of the box without having to know too much. There is, as Alex said, with the MCMC, the basic problem that there's a lot of care and feeding to the algorithm. So unlike our classic regression framework where we can just throw things in and we'll get an answer and we'll know it's at least the regression answer, you can fit these models, and if your MCMC is bad, you don't even know if your model was good or not. You just know that your MCMC was bad and that it's messing you up. And so you could have a very good model and you just didn't let it run long enough or something. And, I'll talk more about these sort of details to sort of get us all kind of in tune. But in general, these sort of simulation techniques are super clever, super powerful, and just becoming more and more important. And so the basic idea, right, is that if we can simulate from an arbitrary distribution, we can then calculate the statistics we care about. For example, say simulating from an ERGM, we could then estimate out the denominator, and then we could do our sort of standard maximum likelihood estimation. Turns out that basic idea is called MCMC MLE, and we'll talk through that. Before I walk through that, I just want to give people sort of a very simple crash course in MCMC. So MCMC, right, is the combination of a Markov chain procedure. So this is where we have some x1 continuing on some state space such that the probability of xi conditioned on the past only depends on the last one. Okay, so that's our so-called Markov condition. We then have our Monte Carlo procedure, and it turns out the definition of this is like goofily simple. It's just any procedure which uses randomization to perform a computation with fixed execution time, but it doesn't guarantee the output. And this is one of those basic problems with MCMC, which is we know at the limit what we're doing is going to work. We never run things for infinity, right? We stop at 100,000, 10,000. And so we just have to trust that we're close enough to infinity. But there's always a bit of faith in there, which is always a little unnerving, or at least I always find it unnerving. Notice that you can compare this against other procedures. I always like this goofy example. Maybe I'm the only one, but I think this is neat. So there's this thing they call Las Vegas procedures, which has a guaranteed output. You will get the right answer, but it doesn't have a guaranteed running time. So yeah, you're like, okay, I've got something that will give me the right answer, but if it's gonna run until the world ends, that doesn't help me. So you can guess which one of these procedures is used more common in the real world. So if you put these two together, you have something where you can simulate from an arbitrary probability distribution. And there's a lot of these algorithms, and people spend tons of time on this, right? The focused MCMC algorithms generate certainly hundreds, if not thousands, of statistics and computer science PhD dissertations. So you're not like expected to know everything or anything. You're just supposed to have, you know, the basic idea enough to use the tools, right? We want to go through and we want to go work on our substantive problem. And so it's good to know some of the names. The Metropolis algorithm is probably the most famous. It's maybe the first really big one and maybe the most general in the sense that you can take a say something like uniform distribution and cut out the probability distribution that you're interested in. So you can get some arbitrary target distribution, say for example in ERGM, using the Metropolis-Hastings algorithm. This is not usually a particularly efficient way to do things. So while you can use this to calculate ERGMs, this isn't how they actually do it in StatNet. They use a very clever Gibbs sampler, which I won't talk about, but it's worth just noting. And StatNet, on top of that, right, so we have this simulation procedure, so we can now estimate the denominator. Notice that the denominator depends, though, on the parameters, right? And we don't know the parameters. So to get the parameters, we need some starting point, right? These algorithms all require you to sort of make some initial guess, and then you just iterate forward until you get something that has sort of meets convergence diagnostics, right? This is sort of a classic iterative procedure. And so this is where we come back to the MPLE. So StatNet starts with the pseudo likelihood estimator for the thetas, and then simulates out the distribution, and then fits the true maximum likelihood estimates of the theta, and then does that a bunch of times. It's got a few other clever things that it's doing under the hood, because the people have been working on this for like 15 years, and like any group of people who've been working on a single problem, right, they build more and more scaffolding, and it's gone from what is a pretty like a super clever idea that's pretty understandable to some pieces that would require way more time than we have in this lecture. But I just say it's got more checks and balances than this procedure makes it sound. Okay, so we now have this very cool situation, right? We've got a probability model for networks that we can interpret at an edge level, where we can put in arbitrary network features, and we can fit it to real data, and then we can interpret it. Now, there's obviously some details I've glossed over. How do we know if the model's good? How do we know if our MCMC is working well? That's basically the next section. So remind me, how long do I have you guys till? Another half hour? Okay. I'm gonna sort of walk through this basic part, and then I'll probably give people a couple minutes, and then we'll go through the model assessment stuff, okay? I've been talking at you for quite a while, so I assume you use a little break. Okay, so we have this basic structure, right? We saw this for the simple logistic case. It's going to follow the same basic thing. So we have our Y, this is our network, and then we have a bunch of terms. And so if you want to know what terms are readily available in the ERGM package, you can go into R and you can type help ERGM terms, and it will give you a laundry list of everything that they've put together. The key basically is this change statistic idea. If you can compute the change statistic, you can fit this ERGM framework. Note that means that this should be extensible, right? And it is. There's an entire package dedicated to taking change score, a function of change scores, and pushing it into the package. So if you find that the ERGM package doesn't have the key network concept that you're really most interested in, you can extend it. It's a lot of work. I'm obviously not going to talk about it in this lecture and lab, but there's a bunch of documentation on it, and if you're really committed and it's important for your research, it's worth figuring out, and if you have trouble, you can always email the StatNet team directly. But they've coded a ton of things, so all your basic things and then some are there ready to use. Basic note, everybody here is like familiar with sort of basic R syntax at this point, right? So when you have a linear model object, right, there are commands for summary, print, plot, that sort of thing. All these ERGM objects have that standard S3 class sort of object property. And I'll talk more about that in the lab. This obviously will get to those sort of details, but it's good to point out. Okay, so let's go back to our flow marriage graph, right? It's a nice, simple network, and we can fit ERGMs to it pretty directly. Okay, so let's go back. We fit our simple Logit model, right? And we get out our maximum likelihood estimate for our theta. We can do summary on it, and we get these sort of standard summary output, right? Our model, the number of iterations it took to compute, our theta, standard error, how much the MCMC is affecting our standard error, and then basic deviance calculations, AIC and BIC. All right, so now let's fit something that requires this autoregressive framework, right? Let's fit something more complex, just a simple triangle. So now when we do this, we get all of this output. And so this is ERGM telling you what it's doing in this MCMC MLE algorithm. It's telling you how many iterations it took to converge, and then some other statistics. And then it'll have this nice warning reminding you that this isn't fit using MCMC methods, and you should go check to make sure that your MCMC methods are working correctly. All right. If we want sort of reasonable output, we can again do our summary on the ERGM object, and so we'll get these same basic details. Notice this model is pretty simple, and so we don't have, like, the MCMC doesn't seem to be causing us any problems. We get all of our otherwise standard output. Notice triangles are not, like, particularly important. The model is saying, you know, you could basically treat it as 0. So just for some more examples, I thought it would be nice to fit this classic P1 model, right? So the P1's for directed data. So have you guys talked about the Samson monastery data at all? So there's this very classic, famous data set in the social network literature where this graduate student went out and was collecting data on a monastery, and there became a rift. 2 groups emerged, and they fought, and then one left. And so people like to use it for especially sort of clustering algorithms, show that you can pick out the 2 groups correctly. This is the liking data, so which monks liked each other. And then we can fit this basic P1 model, right? So we have the edges terms, the sender and receiver terms, and a mutual term. Okay. All right, I'm gonna push through this last little bit and then give you guys your little break. This is just to help aid in adding these complex terms, see how people interpret them sort of standardly. So one of the first complex terms that people like to talk about are in-stars and out-stars. These are, so for the undirected case, right, 1 star, 2 star, 3 star, and just keeps going, right? And then for the directed case, we have out-stars and in-stars. It turns out if you control for the stars, it has this interesting feature that it'll fix the degree distribution. So 1 star will fix the mean degree, 2 star will fix the variance, 3 stars will fix, I think the kurtosis is next. Anyways, you know, these different moments. So the stars can be a pretty powerful term within these models. People tend to interpret them as a type of edge clustering. These are obviously important if you have sort of certain individuals that are, say, getting piled in upon. And sort of like brokerage kind of statistics. And so we can fit the star model. So let's say we just want to fit a 2-star model. We can fit 3-star, 4-star. It turns out in practice, I'm going to talk about this, a very important problem with these exponential models called degeneracy. Basically, if the model is poorly specified or specified in a way that there isn't really a good answer, it will predict everybody to either interact or no one to interact. And they call this degeneracy, and I'll expand upon that. But it turns out the just the stars on themselves on sort of moderate-sized networks tend to have this degeneracy property, as do triangles. So this is sort of the first classic feedback term, right, that people talk about. It's got a lot of important concepts, you know, SIML and stuff in sociology. People really care about three cliques, and it's maybe the most obvious endogenous clustering. And so, you know, people tend to be interested in, say, you know, simple triangles in the undirected case, and then cycles in the directed case, but any of the triad census terms you can put in. And depending on the term, right, the triad census can give you a sense of transitivity or hierarchy. It can give you indicator of extended reciprocity ideas, right? Say you've got some nice chain of islands and you're passing things around. You can look for things like that. And we can, again, fit it very straightforwardly in this ERGM framework. So flow marriage, edges, triangle, which we've already seen, right? We just did this. Okay, so with that, I'm going to give everybody a 2-minute break. I'm sure you need it. I could drink a little bit more water. And I'll see you all in just like 2 minutes. All right, is everybody pretty much back? Oh, yeah, question.
Question one is, can I understand about the 1-star, 2-star as in one thing you just interfacing that way, or is it slightly different?
Sorry, I didn't hear the last one.
1-star and 2-star, can I interpret it as a 1 degree or 2 degree?
Yeah, it's a count sentence, and it obviously relates. You can mass it directly from it.
Okay. And the other one is your summary statistic, there's MC whatever micro-percent of it. It's right now it's going to be 0. But what if we found that it's 20 or 30? I mean, how should I interpret it? How is it influenced by?
Okay, so we're going to talk about that in this next part. So why don't we go through that, and then if you still have questions, if I don't have time to answer them, we can talk about it in the lab, because we'll also do a lot of this MCMC diagnostics in the lab. Does that sound okay? Cool. All right, so we've introduced a relatively complex model, but one that we can fit in software. But we have 3 fundamental problems that we need to focus on. There are certainly a few other minor ones, but we're going to focus on these 3 basic ones. The first is model degeneracy. This is that problem that I mentioned before, that it's sort of a poorly specified ERGM model tends to predict all zeros and all ones. This is not a property of a model we want, right? We almost never expect everyone to interact or no one to interact. And we certainly don't expect it to oscillate between those two. So when the model has that property, we call it a bad model. There's a few ways to handle what that means. The current state of the art is basically this idea that the terms that you've chosen are poorly specified for the network that you're looking at. So one of the things that happened and has happened in the ERGM literature is that a lot of the network features that are focused on come out of very small network analysis. So many of the original ideas were built from ethnographies of small groups. So we looked at, say, windsurfers on a beach, or small communities in various places. And so we have this concept that a triangle is really important, right? That we have these triads, we want to measure its influence. But we don't necessarily expect the triangle to be a runoff feature, right? So when we start looking at networks of 100, of 200, of 1,000, we may expect the triangle effect to be very local, not expansive over the whole network. So when we fit these simple triangle terms, this just census of all triangles in the network, and try to use it to model the probability of the network being observed, it can have some sort of unintended consequences. And one of those unintended consequences is this issue of degeneracy. And so people have started to solve this problem with hierarchical models. So not something that we'll see today, but something you might want to look into. There are hierarchical ERGMs, so where you can constrain the sort of sub-communities in the network and then look at these local effects in that community. And then people have also tried introducing new statistics. So in, say, for example, the ERGM terms, you'll see a local triangle effect, so one that doesn't have these runoff properties. Other ideas are weighting terms. So, for example, there's this thing called GWESP, which is geometrically weighted shared partners. So we might imagine, right, that our first shared partner should really affect our likelihood of an edge, but the 1,000th shared partner should have much less of an effect. So we have just sort of a decreasing influence in the counts. And these have also been shown to help with this degeneracy problem. So with that in mind, I want to show you a couple really classic plots that Mark Hancock put together. So Mark Hancock went back, and as I said, right, up to a network of size 7, you can compute all possibilities, and you can compute the actual maximum likelihood estimate. And what Mark showed was that in the parameter space for, say, the 2-star or the triangle term, the likelihood function is pretty ragged. It's very easy to have a bad case. And so this basic idea extends, and this is where Mark introduced this idea of or sort of coined this term degeneracy for the network models. I should point out these issues of degeneracy are a general problem in exponential family models, and so it's not like it was created just for the network case, but it was coined into the network literature. Okay. The next basic problem that you can have, right? So assuming you have a well-specified model, it's the correct model, it's going to answer all of your questions and problems, but you can still have it not work by having your simulation fail. And the simulation can fail in a lot of different ways. So obviously, if your model is just bad, it can fail in the sense that your simulation will just predict things that are unrelated to your observed data, and we'll talk about ways to sort of test that. But the other ways that it can fail is just your MCMC algorithm being bad. And so this is examined using the CODA library in StatNet, and has all the issues that Alex was talking about earlier. Right, so we fit our ERGM object, and then we can use MCMC diagnostics from the CODA package. So this is pretty cool, right? People have designed lots of standard ways to check this, and you can just go and use them. Lots of times people like to use things like the Raftery-Lewis convergence diagnostic or other statistics. There's a bunch of them out there. Pick your favorite one. You can also go and plot these statistics directly yourself if you really want to. This is just a note for those people who want to know where it's hidden within the ERGM object. So right, we fit, say, the flow business network with edges, and then K-stars and a triad term. And we get out this sort of standard MCMC plot, right? And this is one that's working pretty well. We'll see in the lab some ones that don't work well. But this has sort of that standard white noise feature you want to see, right? This shows that your Markov chain is mixing well. If you see something where it's like going off like this, your Markov chain is not mixing well, that's bad. It shouldn't have any structure, right? When we think back on the MCMC theory that we talked about, right, it should only depend on the past, and so you should just see this white noise movement. And then we can look at sort of the general distribution of our parameter estimates, and we don't want to see anything super wonky. It also, when we run, besides this sort of standard trace plot, it also spits out a ton of statistics, so we can look at the mean, standard deviation, the naive standard error, the temporal correlation. We can look at the cross correlation between the terms. We can look at how well the chains correlate across. Obviously, we want this to be kind of low because we're expecting a certain amount of independence. And it gives sort of the standard Guecki statistic. Anything else? Yeah, and it just, just reams of these things. This is mostly for the lab. I just want to get people to see the framework. Obviously, we're going to dig into this over the next hour and a half after this, but it's good to just see what the basic output looks like. So the key here, right, is we have our MCMC parameters, and sometimes we have to scale them up, right? Sometimes we need chains of 10,000 or 100,000. Sometimes we need to sample at larger and larger intervals to get the properties we want. Sometimes we need to throw away more data, right? We don't want the start point to affect our estimate. So to guarantee that the start point, that it's so-called memoryless, we throw away a lot of data. So sometimes you need huge burn-ins. And some of these models are much harder to fit than others as far as the MCMC model goes. It turns out ERGM, you can basically control all of these things in the MCMC and the MLE fitting if you want. I don't necessarily advise digging into this too deeply. Obviously, focus on the classic basic things. But for those of you who want to know, the key for all of these terms is in the control.ergm. So if you do args on a function, it'll spit out all the arguments it can take. So it's just a way to see all of the arguments in one glorious slide. And I think it goes actually a little past the slide. All right, so all of that assumes that your model is a good representation of the data, right? Well, how do we know if we have a good representation of the data? We don't have sort of a classic simple R-squared measure where we can say, yep, it fits the line pretty well. So we're going to have to do something else. And here, people working in the ERGM literature have borrowed heavily from these sort of concepts of posterior predictive checks. So the basic idea here is going to be, if we take our probability model and we simulate from the probability model, will the network statistics of interest be covered well by our probability model or poorly? If they cover it well, say, perfectly in the median of the statistic and then around on each side, we say yay. If it just barely covers it, we say, well, maybe we can argue our way through it. If it's nowhere near it, we're like, oh, this property I really care about, my model's terrible. That's bad. What am I going to do? I'm going to have to reconceptualize what I'm looking at. So how do we do this in StatNet? Well, it turns out they've very nicely written a function to just do this procedure. Notice it depends very heavily on the MCMC, right? The MCMC tells you how good a quality your simulations are going to be. So first check your MCMC diagnostics, verify that that's working, then run your goodness of fit. Goodness of fit takes our ERGM object, and then there's some standard ones that'll fit if you just pass your ERGM object to the goodness of fit function. But you will actually can take arbitrary terms, okay? So that's pretty cool. So let's look, for example, at ERGM flow business with just a simple edge model. It's spits out some statistics, and then the key thing is sort of these visual plots, right? So what we see here, for example, is the degree distribution from our simulated network, and then we have our observed degree distribution. So for example, we're way underestimating the number of degree 0. We're underestimating we're overestimating the number of 1, 2, and 3 degrees, though the model does generally kind of track with it. Edgewise shared partners, we're not doing well at all. And then the geodesics, we're not doing terrible. You know, that sort of idea. So what can we do, right? We can add more terms, we can dig into the model, and ideally, right, we find something where the median black line fits the data point more or less exactly, and then we cover, say, the 95% around. That's usually almost impossible to find, so we look for sort of, are we capturing the key network statistics for the theory that I'm working in, right? If triadic closure bias is a thing that really matters to me, I'd better be capturing the triadic closure bias. If I'm not doing that, then maybe I need to go back and rethink about my model. So there's 3 basic strategies. One is to keep adding terms, right? Maybe what we're really missing is some key exogenous covariate. Maybe there's gender homophily going on, or racial homophily, or grade homophily, or something else. Maybe I just haven't thought about the right feedback term. Maybe there's a temporal effect. For example, in these sort of models, you can fit an AR1 process really easily, right? We could, if we have, say, 2 time points in a network, we can stick the past time point in a covariate, and it'll fit that. Maybe we've added a term that shouldn't be in there, so maybe we need to pull back terms, right? This is oftentimes where, say, using a BIC or AIC criterion becomes kind of useful. We can fit a bunch of different models, select by, say, BIC or AIC, and then go and see if our goodness fit statistics work pretty well, and then sort of iterate back and forth. Or maybe we don't have to do anything. Maybe we capture the network statistics that we really care about, and the fact that the model isn't perfect isn't going to bother us because we know that for the theory that we want to test, we get it good enough. And so maybe we just stop. You have to get down to your own argumentation. As with any good research, right, everything's built on the foundation of your argument and what you can sort of prove. And so the model's a tool, right? And so don't get stuck in the model iteration process forever if you've found something that will answer your question. So think about this. There's a lot of details here, and we're going to obviously talk way more about this in the lab. I've got you for 90 minutes. We're going to work through sort of the standard StatNet tutorial. It'll reiterate a bunch of these key points very nicely. And then I put together some health-related network data for you guys to play with and try ERGM modeling on your own, and I'll individually kind of work with each of you at that point. Okay, does that sound pretty good? All right, so a couple last notes. The StatNet wiki page is great. There's a million references to people who've published using the StatNet software and ERGMs in general. There's a special issue in the Journal of Statistical Software on StatNet, which can be a very, very useful resource. These slides themselves are actually a giant compilation from 5 courses, Carter Butt's 2009 analysis of social network data, Mark Hancock's 2011 statistical analysis of networks at UCLA, Peter Hoff's excellent statistical analysis of social network slides that are all available online, Martina Morris's great social network class, and then also some of my own ideas. And so with that, I think I have a couple minutes for questions. I'm relying on Jake back there to tell me if that's true. Or am I done? Okay, so any basic questions? Yeah.
I just have a question about packages for two-mode and multiplex ERGMs and where R is on that versus MPNet, like using MPNet packages for more than two-mode.
So two-mode networks are pretty well handled in ERGM because a lot of the people who developed it specifically for sexual contact networks. And so all the bipartite terms are pretty well implemented. Some of them are not named so obviously, so it can take some digging into, but it does that really pretty well. Multiplex networks is more complicated. It really depends on what you mean by that. You can do simple things in the ERGM function itself in the sense that you can regress one network on the other pretty straightforwardly. There's some great work by Pavel and Carter for doing certain things with multiplex networks, and there's sort of draft software floating around for that. And there's a handful of other things out there. Do you have a particular example case you're thinking of?
Well, yeah, I mean, so I'm working with multiplex ERGMs using MPNet. So wanting to condition, say, like you have Facebook networks and you have Facebook friendships and Facebook group memberships, and you want to see the interaction between, like, is Facebook group membership, like co-membership, conditioned on also being friends. So not going beyond just using one as a covariate, but actually modeling them together and interacting. So I've only been playing around with MPNet, but I just wasn't sure where R was on that, because I mean,
So
the whole ERGM world seems to be moving towards R anyway, but I just wasn't sure.
Well, let me make sure I understand the problem correctly. So you have a block model network and a social network. Like you have Facebook friendships, and then you got some sort of group attribute that they
And I
join.
have a group membership. So we have two types of tie. I have a two-mode tie, which is the Facebook group membership and Facebook groups.
Oh,
And then
I see.
I have Facebook friendships as well.
Okay, and so you want to model both of those simultaneously. You could probably very, very carefully cast that into the ERGM framework, but it would take some thought. I don't know of any readily available software for just plugging that in. I know Carter has some draft software for Bayesian version of this multiplex problem that would certainly work, but you'd have to email him, and it may not be in like a user-friendly way at all. I suspect it's not, because I don't know if he's even got around to publishing the paper on it. I don't know of an easy way. If MPNet has a like straightforward way for doing that simultaneous multivariable problem, that's probably going to be easier. All right, I'm told to cut it off. I've got you for the lab, so if you have more questions, feel free to ask them then. Play around with the website. If you guys have GitHub, play around with that. If you don't, I'll sort of talk through why it's neat, and you should have it, but I'll show you how to get everything without it.